In this lecture, we are going to discuss stationary states in quantum mechanics. In order to do so, we start from time-dependent Schrodinger equation, which is written as iota h cut curly psi over curly t equals minus h cut square divided by 2m curly square psi over curly x square plus v psi. If we solve this equation, we can get information about the wave function psi, which is a function of position and time. Now, this is a partial differential equation and can be solved using separation of variables technique. Therefore, we can write this big psi, which is a function of position and time, in terms of small psi or lowercase psi and phi, where the lowercase psi is a function of position only and phi is a function of time only. Therefore, the above equation can be written as like this, where we can write this this term curly over curly t into psi phi is psi d phi over dt, in this term is d square psi over dx square into phi, as phi is a function of t only, so and psi is a function of x only. Therefore, partial derivatives are now replaced by full derivatives in these terms. Therefore, equation 2 can further be written as iota h cut psi d phi over dt equals minus h cut square divided by 2m d square psi over dx square into phi plus v into psi phi. Now, if we divide this equation by psi and phi, the product of psi and phi, we get iota h cut 1 over phi d phi over dt equals minus h cut square divided by 2m 1 over psi d square psi over dx square plus v. As you can see, the left hand side is time dependent only. It depends only on time, whereas the right hand side depends only on x. Now, in order for this equation to be true, both the left hand side and right hand side must be equal to some constant, and let that constant be e. So for the left hand side, we can write iota h cut 1 over phi d phi over dt equals e. If we bring iota h cut and dt on this side, we can solve it for phi by integration. So phi then becomes like this, phi of t equals e power minus iota et divided by h cut. Similarly, for the right hand side, we can write minus h cut square divided by 2m d square psi over dx square plus v psi equals e psi. This equation, which depends only on x, is known as time independent Schrodinger equation. It has got many solutions, that is psi of nx, with corresponding energy eigenvalues e of n. So using these solutions and solution for the time dependent part, the total solution to equation 1 becomes psi of xt equals psi nx e power minus iota e nt divided by h cut, where one particular solution of this may be written as psi of xt equals psi x e power minus iota et divided by h cut. As we have got the general solution to time-dependent Schrodinger equation, we are now in a position to discuss properties of any particular solution to this equation. So for any particular wave function, psi of xt equals psi x e power minus iota et divided by h cut, if we compute its probability density, which is psi xt mod square or psi static into psi, by plugging this value over here, the exponential terms cancels out, so we end up with psi x mod square. So although the wave function itself, as you can see, is time dependent, its probability density does not depend on time. Such states are known as stationary states in quantum mechanics. Similarly, the expectation value of the Hamiltonian is defined as psi static h psi, and then if we integrate this by plugging the value of the wave function again, we end up with psi static h into psi. So as you can see, the right hand side again is in the special part only. Therefore, it can be concluded that the expectation values of any physical observable with respect to stationary states are also stationary. Similarly, another property is they are states of definite total energy. So if we compute the expectation value of the Hamiltonian, which is defined as the integral of h psi psi static h psi dx using Schrodinger equation as h psi equals e psi, so we get e psi static psi dx, or integral of psi mod square dx, that is the overall probability is 1, so we get e. Similarly, we can calculate the expectation value of h square according to the same technique. which is equal to E square. So if we calculate the variance of the Hamiltonian, which is defined as h square minus h average whole square, then it becomes E square minus E square equals 0. Therefore, the distribution has got zero spread. This means that measurement of the total energy will always result in E for stationary states. The most general solution to time-dependent Schrodinger equation can be written as psi of xt equals summation n equals 1 to infinity cn psi of nx e power minus iota e nt divided by h cut. In other words, it can be written like this, where psi of nxt equals psi of nx e power minus iota e nt divided by h cut. Thus, the most general solution can be written as a linear combination of solutions psi 1, psi 2 up to psi of nx with corresponding energies E1, E2 up to E of n. So, if we have more states with different energies, then the exponential parts do not cancel each other out. Therefore, the expectation values in this case are time dependent. Therefore, we can conclude that separable solutions itself are time independent, that is, they are stationary. However, the most general solution is both space and time dependent.